Good afternoon, everybody. My name is Rod Bogart. I'm the principal color scientist at Epic Games. By way of a little bit of credibility, hopefully, I'll tell you about my history. I was at ILM for 10 years, then I was at Pixar for 9, I was at HBO for 4, and I've now been at Epic Games for 5. But more importantly, my initials are RGB. So I have to do this. Now, I often hear from people that they know enough about color pipelines to be dangerous. Our goal today is to make you safe. So we're going to talk about color pipelines and the specific color transformations that happen in the engine and during rendering. And to do that, we're going to imagine a simplified render pipeline. Now, in this, we have texture input, we have our linear rendering that happens in RGB, then we have post-processing, and at the end, we display our pixels on the viewport, or possibly save them to a file. Now, we're going to start in the middle rather than the front to talk about linear rendering in RGB. Now, the first thing to note about a color value is that color values represent an amount of light. And since that's true, those values can have a large range of very, very bright values, or they can be really small values, and they are also linear, which means if you double the number, you double the amount of light that that value represents. And finally, these RGB values are in the working color space. And we'll get more specific on that in a little bit. Now, before we continue to the rest of the pipeline, let's talk about linear and RGB. So to do that, we're going to use the next 10 minutes to do about a semester of color science. So when we say linear RGB, it's telling us two important properties of the color value that we have. And those are the color encoding and the color space. Now, many people, when they say the words color space, they include the notion of color encoding, and to be honest, I'd prefer that you not do that. If you can, try to keep them separate because they're distinct from each other and they both matter independently, and you need to keep track of them in the engine. So first, we're going to talk about color space, and we'll do that with the RGB color specification. Now, there are other color specifications, and typically the things that they all have in common is that there are 3 values that somehow specify a color. And you could specify the same color possibly in all of them, but there's a way to transform from one to the other. But because we're doing rendering, we're doing RGB. And rendering in RGB means that we have 3 vectors. We have a red, we have a green, and a blue, and they're all perpendicular to each other. And you can imagine that they're also independent. That's actually super helpful, that when you change the red, it doesn't adjust how green or blue the thing is. Now, when they go from 0 to 1, you get a color cube. And they don't have to stop at 1. Remember, we were talking about high dynamic range values earlier. So they can go past 1 and become much bigger, and so this cube can extend beyond. But for the purposes of this right now, let's just think of it as this little box from 0 to 1. That's a portion of the RGB color cube. But that doesn't tell us very much, because which RGB is it? There's a bunch. So there are different color spaces that define which RGB you have. And so here's a list of some of them: Rec 709, BT 2020, DCI P3, Adobe RGB. You see these in images, that the image is possibly tagged as having one of these color spaces. You also see this with displays. The displays have different capabilities where they can say one of the color spaces that you're currently doing. And so those are pretty common. Now, to distinguish between 2 different color spaces, one of the things, two different RGB color spaces, the way that we compare them is using XYZ, which is another specification. And so this is the Rec 709 color space specified in XYZ. You can still see that it's a red direction and a green direction and a blue direction, and they're kind of independent. They're not perpendicular anymore, but that's okay. What this is really telling us that there are values outside of 709 that do exist, and those might be in some other color space that we're going to deal with. And we also see that the shape is like a cube there, but also there's a triangle in the CIE color diagram. And in that case, what we're really showing is just the chromaticities. Those are those little numbers up at the top of what color red is, what color green is, blue, and white. And we're very specific because Rec 709, if you ask for red, 100, that's the color red you get, and it's a very specific thing. Now, we can add on top of this what happens with the Rec 2020 color space, which is typically called a wide color space. And you can see that it is in fact wider. It's a bigger box, so it entirely encloses that 709 thing, and it's also a bigger triangle. And so you can see that both of them make it clear that 709 is kind of a nice size, Rec 2020 is even bigger. And so let's talk about how we might compare those two. So as I mentioned before, images and displays can have their own color spaces. So what happens if they don't match up? So if you have a 709 display and the image data is 709, it looks like this. But if you have a 709 display and your image data truly was properly created for Rec 2020, it ends up looking kind of desaturated because that data wishes it was on a very saturated display and you didn't do it right. You displayed it wrong, and so you ended up with a desaturated image by looking at it on a 709 display. Now, the more common mistake that people make, and I suggest you do it because it's interesting to see, is you can have your 709 image and your 709 display, and then you say, well, I'm going to reach on the back of my television or monitor or whatever, and I'm going to set it to something else. And so in this case, we'll set the display to be a 2020 display. And when we do that, then the image comes out really, really saturated because we've pushed those colors, they were 709 colors, and they're out into that bigger triangle. And so here, one of the things that you might have noticed is that the 3 ball, which is the red one, seems to move a long way. The difference between that red and the other red, the 2020 red seems like it's moved a lot. And the greens moved a fair bit and the blue not so much. And when we look at the CIE diagram, it's kind of counterintuitive. We look at this and we realize, well, it looks like the green is the one that's farthest away, and the red's kind of not that far, and the blue's super close. So why did the red seem to move the most? Well, as it turns out, the CIE XYZ color space projects into the XY color space, the 2D, and it's not very perceptual. And so a preferred perceptual diagram is to use the U prime V prime plot. So if you do it this way, we can see that it's the same data. It's just kind of shifted up and a little bit. But now the red is the one that looks like it's going to move the farthest, and the green is going to be moving kind of the mediumest, and the blue is the small. And this is nice because in the event that you are having dinner with one of your color science friends and you want to impress them, make sure that you use U prime, V prime plots. That they'll actually really love that. Now, after looking at this for a while, we might actually look at this and say, you know what? I really like the way the saturated one looks. Don't do this. Whenever possible, we want to ensure that the intended colors are being shown properly. So if you mean to make it more saturated, use some sort of control that makes it more saturated, but stay inside of the space that you're supposed to be in. So we did color space, and that is the thing that tells us what color red is, but color encoding is what tells us how much light we have. Because when we encode these values, in rendering, we're going to be doing it in linear. But if there is a color encoding other than linear, we have to keep track of how bright the values truly are. And there are some other encodings. They're in images, they're in signals and displays. And so in images, you might see it with PNG, JPEG, MP4, and EXR have different ways of encoding the data so that it can store it at all. Floating point is really good at holding linear data, but little bitty numbers like 8-bit values are not. And so you would prefer to have some sort of encoding there. And we have the same problem with signals. As you go across a wire, it is not a high bit depth thing. And so HDMI and all these other things have some sort of encoding on them for the imagery to get across. And then when you're finally at the display, it probably handles a certain set of encodings as well. And here's a set of what some of them are. And some of them are based on some of these needs, like linear and sRGB and PQ, and gamma is a common one. But even camera log, that is a way of storing light values in some other encoding. Now, when we talk about the representation of light, because that was what we were talking about here we have 0 to 255 just plotted kind of straight across. And so the minimum value is off, and the maximum is as bright as this particular device can go. And one of the questions we might ask ourselves is, well, what happens here at the pixel value in the middle? How much light is that? And as it turns out, it is not 50%. The response is much more like this. And this is called an EOTF, an electro-optical transfer function. The electro is the code value that you're sending, this pixel value. The opto is the part that is how much light you get. And so the comparison between those two is the EOTF, and you get a curve. And so in our case, here, that halfway value, that halfway pixel value, really only gives you about 20% of the overall light output. But it does another great thing, is it has a lot of interesting numbers across the darks. As we go stepping through individual small changes to our pixel values, the amount of light changes very subtly, because actually that's what our perception does too. And so we need to put the numbers in the right place so that when we use little bitty numbers like that, we can actually change it. And so we need some sort of curve like this. And in this particular case, this color encoding is called sRGB, which is unfortunate because when we saw earlier, there's also a color space called sRGB. So we need to keep track of those two separately. So let's go back. This semester is over. Congratulations, you all passed. We're going to go back to our simplified render diagram here, and we're going to see where sRGB terminology might come up. And one of them is in the working color space. So there is one, and you can set it in your project settings. And by default, the default is an sRGB color space. Color space, not color encoding at this point, color space, because it's linear. And there you see the chromaticity values that we have, and that list is exactly the same list of values that I showed you earlier when I was talking about 709, because they're the same. The 709 color space and the sRGB color space are exactly the same one, which is why here we tag it that way to actually clue that. So that the preference is when we talk about sRGB in the engine, we're almost always talking about the sRGB encoding curve, which we're going to talk about a little bit further. But the color space only shows up a couple of places, and so we try to couple it with the fact that it's also 709. Now, there's some other choices. You could pick things as your working color space that are different than sRGB or 709. And so you can have Rec 2020, which was that big one we saw earlier. ACES CG is a common choice. A lot of people like that. But you can even have custom and specify your own chromaticities if you really want to be daring. So the working color space isn't the only color space that happens in the engine. It's the main one, and it's the one that most of the work is going to happen in, but we might come into and out of the engine and have a couple places where we have to deal with another color space. And where's that most often happen? Well, it certainly happens at the beginning. Your texture can be in a different color space, and it can have an unusual encoding. And on the output, your device that you're displaying to has its own color space and may have its own color encoding. And so those two transforms are certainly there. And these are the places where the engine is going to do some work. So let's talk about texture input first to see what happens during texture input, because actually it's a fair bit of stuff. When you bring a texture into UE, it has a few different states. There's the original file that you drag in off the desktop, and you drag it in and it becomes a U asset. But the U asset and the original file are not what are used on the GPU. The thing that is GPU usage is the platform format. So this first step, which is drag it in from the original file and convert it into a U asset, its goal is to not change very much. It's basically trying to embody the file into the U asset in the same state that it originally was. And mostly that's what it does. There's a couple of unusual cases. If, for example, you had a 10-bit file and you brought it in, it's going to get promoted to 16, but comfortably. It doesn't get changed, and so there's no color conversion during this step. Now, the reason we have that step is because then when you go into the texture editor and start messing around and making different versions of the thing that's going to go on the GPU, we have to go back to the US edit all the time to re-encode that. And so those conversions happen quite often whenever you make changes to those parameters. And the other thing that happens is that that USET is your original data probably doesn't have mipmaps, but you want them for your texture sampling, so the mipmap calculation happens here too. And our final goal is that all of our data inside the engine is in the working color space, so that conversion happens here too. So when you choose a choice for what your platform format is going to be, we call that compression settings inside of the texture editor. You have a choice, whole list here. And for RGB, there's a bunch of them that happen for very specific targeted reasons, but for RGB, there's basically two. There's two groups. Integer ones, like default, which is BC1, but also the floating point formats that have 16F there. And there's different ways that that happens to get compressed, including even a 32 float, if you choose to. But if you have a texture that you know a lot about because you made it, or maybe it was made from a special camera or something, you have ways to override the default behavior. You can say what the color encoding is, because color encoding and color space matter. So you can say what the color encoding is, and you can see the pull down there has a lot of choices for what that curve might be. And you get to pick so that you ensure that the proper linearization happens later. And then the color space defaults to none, which means that if you don't do any override, and then it's assumed to be the same color space as your working color space. But you can also pick one, and then it will do an explicit conversion. Now, as it turns out, there's more steps in there, so let's broaden that out a little bit. And the steps really are that the conversion is linearize to the working color space. So the linearization is take off the encoding. Convert to working color space is go from whatever the color space of the texture was to working color space. Then do all the mipmap calculation. And this is the right thing to do because mipmaps need to happen with linear. Just like all of the rendering math. Almost all rendering math needs to happen with linear values. So the mipmaps do that too. And then after that, we convert into the platform format that we're going to use. And that's how we get stores. And so this is the way you do that, right? You have some compression settings and you choose something off that menu and it's one of these items. And then, but it's not the only thing you have. You have another parameter down here. And we also have, well, this. And you probably wondered, what's it do? And it says sRGB on it. So it's the working, no, it's not the working color space. It is a color encoding space. And what this does, when we go back to this sequence of steps here, is the sRGB flag really controls this last step. So in the end, the platform format that goes onto the GPU can be in one of two encodings. It's either linear, or it's stored with an sRGB encoding on it. Those are the two. Those are the only two choices you get. And that flag, that's why it's a toggle, is it's either sRGB or it's linear. And that's what does that. That's what that flag is for. So let's look at an example of this in use. So if we drag in this, I've kind of cobbled together two user interfaces here. The thing on the left is from the texture editor, and then the rest of it's a material. And if we drag in a PNG file, there's three things that are really important. There's what the compression settings are, there's that sRGB flag, and then there's which way you're doing it, the sampling. So the sampler step, in this case that one's set to color, those three kind of have to coordinate for things be happening properly with your texture input. And so let's say that for some reason we decided to intentionally make a mistake and turn the sRGB flag off. And so that's the thing on the bottom. And I did it, so I turned the sRGB flag off, and I left the sampler as color, and we get an error. It says that doesn't match, and it's not kidding. Sometimes errors are telling you the truth. It actually thinks that that sampler can't be done because it doesn't match up to what you're trying to do. So, and it also changed the picture a little bit. So we'll change the sampler type to linear there, and that helps, but it makes the picture wrong. because, as it turns out, the sRGB flag was doing one other thing. So I lied a little bit. What was happening with the sRGB flag is it definitely controls that GPU state, but also by default, for certain file formats, it also decides what the linearity is. Now you can override it with those color encoding settings that we had previously. But if you don't, then that sRGB flag also tells you that this is an EXR file, so it's probably turned off. This is a PNG file, so it's probably turned off, on, and so it's going to give you the proper linearization. So while we're making mistakes, let's make one more mistake and go and override that capability and say, well, I know that the encoding is sRGB, so I'm going to set that in my override, but leave the sRGB flag off and leave the sampler type as linear, which I can do, and now they sort of look like they're the same, but as it turns out, they're not. If we get in close here, we broke the image. So what happened? We took our data, we linearized it, we mip-mapped it, and then we took that linear data and we stored it in 8 bits. Don't do this. 8 bits is not enough room to store linear color data. You need something else to keep track of the amount of subtlety that goes on across the bottom of what the colors are when they're dark. And so 8-bit linear doesn't work out. So we're going to come back to where our color transforms happen. There's the 2 at each end. There's also something around this neighborhood, which is more artistic color grading and also an overall look, and we'll get into that in a minute. So it's more fair to say that there are more transforms, but those are the major ones that you're going to see. Now, when we're all done with rendering, and we did our shading, we did our lighting, that culminates in something called scene color. This has everything in the render basically done. But you might ask, are we finished? And we're not, because we have some more things to do, and those are going to go through our post-processing step. So what is left to do? Well, there's a lot of post-processing operations. There's motion blur, that happens late. There's anti-aliasing. As it turns out, that original render was a single sample per pixel. That's all it can possibly do. And so there's super resolution if we're going to up-res. Artistic color grading that you may choose to do yourself. And then there's a whole group of things that are the camera emulation features, including depth of field, exposure, white balance or color temperature, bloom, vignette, filmic look. All those things are trying to emulate what a camera might do. And it's why games look good kind of out of the box with Unreal, is because all these things are turned on. And so as each pass happens in this list that we're going to see here, scene color is going along getting modified. And so let's stretch this out so that we can see what the passes are, in fact, are and what order they're in, because that's kind of important. Now, as it turns out, it's not the camera emulation thing happens at the end. You wish it did, but it doesn't. Depth of field has to happen earlier. And there's good reasons for this. Many of them are for efficiency, but there's a couple other reasons about what happens during anti-aliasing and up-resing, that some things need to proceed and some things need to follow. And so these are kind of the major passes of post-processing. Now, we're going to get into more of the color operations or the color transforms that the engine does, but let's look where you have some control. And the way that you do that is that you have post-process materials. And so post-process materials, here's a list of what they can be. They can be at a number of different places, and these 4 are the ones that modify scene color, because remember, it's moving across as we go from step to step to step. And so these are at certain locations. And so I'm going to tell you what those locations are, and we're going to actually read some of the documentation associated with them to learn a little bit more about them. So the first one is scene color before depth of field. And in older engine versions, I think this was called before post-processing, but now the naming is a little bit more consistent with the actual steps. And a couple of things are hinted here that are good to they're worth reading. It always runs at the rendering resolution. Now, what does that mean? Well, we did a render and it had a resolution, and during TSR or TAA upres, we're going to change that resolution to a new one for display. So there's a render resolution and a display resolution. And so when we're on the front side of TSR, we're at the render resolution. And that's the res that we happen to use when we're doing depth of field. The other thing that it mentions that I think is good to notice is that the input and the output are also in the linear color space. And they're in fact the working color space. And so all those values that happen during depth of field are happening on linear values. Now, the next one is right after depth of field. And it gives you another chance to do some modification because maybe you want the depth of field in when you do whatever it is you do, because it's your material, you can do whatever you want. But it, again, rendering resolution, linear values. The next one is called before bloom. And this might have had the term before Tonemapper, but strictly speaking, that isn't where it is. So it's before the bloom pass. And it runs at the display resolution. And so that's because TSR preceded it. And it's also still linear values. And then the last one, which is, as it turns out, is the default that you get whenever you ask for a post-processed material, is after tone mapping. And it runs at display resolution, but the inputs and outputs are kind of different color spaces, and it's a little bit hand wavy. We'll talk about that in a second, but let's do an example. So here I made a post-processed material that simply does a multiply by 0.5. So it's going to try to bring it down to stop, which may or may not be the right terminology depending on where we apply this. So we're going to show it at before bloom and after tone mapping. So we have an image. And if I apply a scene color before bloom post-process that brings us down by 0.5, what we see is the original image had bright highlights that were rolled off because of the tone mapper. And so they look pretty good. It's not all clipped and weird looking. And as it turns out, those highlights are still there because those values are so much above that bringing it down one stop didn't actually take us all the way out. And so, but the whole scene looks like it went down kind of correctly. And then the camera shows it. If we do it after tone mapping, everything just gets dark. And the highlights become gray because the roll-off has already happened in the tone mapper. And the end result is, now we're just taking those final pixel values that were ready for display and ruining them a little more because we give you that flexibility. I hadn't thought of it that way until now. And so you have to be careful on what you do with after tone mapping because you're not operating on linear pixels there. You're operating on something else, and we'll talk about that a little bit further. So these are the places you can do this, and you have your arbitrary changes where you have control over what happens to the color. And when you modify it, then that next pass will receive what you changed. Now, along the way, I mentioned the tone mapper a three times there, and we should probably cover exactly what's happening there. Now, one of the most common questions I get is, how do I turn off the tone mapper? And it's possible. You can use a show flag to set the tone mapper to 0. You can use a post-processed material to replace tone mapper. But as it turns out, I don't recommend these because it might turn off too much. And this is why. The tone mapper is a whole bunch of steps. It's not one thing. It's these things. Tone mapper has bloom, exposure, vignette, white balance color, or color temperature, expand gamut, color correction, filmic tone curve, and the output device. All of those things are in the operation we call the tone mapper. So if you turn it off with a show flag, none of these are on. But because you hate the tone mapper, I'll teach you how to turn it off one step at a time. So let's recall, though, that the camera emulation features, most of them are tone mapper features. The exposure, the white balance, the vignette and the bloom and all those things, those are in the, and so what the tone mapper's main job is camera emulation. That's really what it's trying to do. But depth of field is kind of its own thing up somewhere else. So it isn't all in there. Now, let's say that we want to turn it off, as I suggested. And for bloom, it's easy. You just set the intensity to 0. And you might want to stop me here and say, wait, there's a bloom pass. So what's the deal? So that bloom pass, the one that's right before this tone mapper, is the one where it calculates how much bloom there should be and what it's going to be, but it doesn't get applied until the tone mapper. So if you turn it off this way, it actually also doesn't get calculated. But that's why the before bloom step exists with the post-processed material is so that it figures out, using the pixels that you've made, how much bloom to do, and then applies it afterwards. Likewise, you can set the exposure to be null, essentially, by setting it to manual, setting the exposure compensation to 0, and also turning off the physical camera settings. But if you set the exposure compensation up to 1, then it's a stop brighter, -1, stop darker. Vignette, easy enough. Turn the intensity off, you can have that off. And then this was the one that you probably meant to do all this time. And that's down in the MISC under color grading. There is 3 values that mostly you mean to turn off the tone curve amount, set that to 0. Now, if you look on the internet how to turn off the Tonemapper, most of those questions are from back in the 422 days. And actually this feature wasn't there. So they're not wrong. You couldn't turn off the Tonemapper back then. It wasn't until 425 where we added a tone curve amount value that you could change. But now it's there. You have availability to that. You can now basically have linear data coming back out, and then the rest of the stuff can happen. And so what remains once we turn off all of those steps by hand, we're basically saying, I don't want any camera emulation features, but I still want some artistic controls because I want to be able to do white balance, and I might want to do some color correction. All those things are available to me, and I should still be able to do them as a user. And as it turns out, there's one more step coming after that. But we just did something in 5.5, is we made a new color grading window. And so all those color grading controls are now unified into one window. And so over on the left there, you see that it's selected one post-process volume, but you could have a list of them and toggle between them and then set the controls differently. So this is super handy and way better than the way it was. The other thing that can go in there is color correct regions will also list in that thing. And so you can still control them. And so you can toggle across the top there, whether it's global, shadows, midtones, highlights. That's really easy. And then all the controls are available to turn on. On the right, you can see some other things that might affect the way things look. And that includes the color temperature, that's in there. The definition of where highlights and shadows really is. And then that tone curve amount, that's also right here if you need to modify it. And I'm going to go on a little bit of a rant about the bottom item here. There's something called a color grading LUT. And this is a thing that you want to work a certain way, and unfortunately it doesn't work that way. And it is a LUT which basically happens at the same time as the post-processed material after Tonemapper. You've made display pixels, and then if you want to modify them a little further, improve them, you can put a LUT there that does that. But it's not operating in linear space. It doesn't maintain high dynamic range. Things have already been tone mapped or clipped off by that point. And so it's not great to be using heavily. If you want to do that, you're better off doing something in a material node. So the other thing that is still there is the output device. And the output device is that last purple step. And it is the thing that makes the pixels ready for display. And so they're ready to be shown on a monitor or maybe even stored in a file. And typically, the most common thing that it does when it does what it does is it's going to do the sRGB encoding curve, which, again, sRGB shows up again here, because that is going to make 8-bit pixels that are ready to be seen. Now, it's not always that. If you're writing out a file that happens to be an EXR, then the output device is linear. It doesn't do any transformation from linear to linear, even if it has the tone curve on it, it still needs to keep that linear values and go into the EXR file. And then the last case is in the event that you do something with HDR. And the HDR settings are much more complicated, and I don't have slides for it. But they also end up with a different encoding and possibly a different color space that you would target. And that happens in that final step. So these are the places that all these color conversions happen. When all's said and done, at the end, then we end up with pixels that are going to get displayed in the viewport. And so the conversion at the end there, those prepare them so that the final step of the Tonemapper is called the output device. And normally, all these steps are turned on. So that's the default of Unreal. And the reason is because camera emulation is present and we want you to have access to it. And so it's the thing that does all that camera emulation effects and also prepares your pixels for a normal sRGB encoded display. Now there is another option. You can choose to use OCIO. And that stands for OpenColorIO, and it's something you can read about because it's not something that we created. It is an open source project that is managed by the Academy Software Foundation. And they have a number of configurations that are available that will allow you to do different kind of transforms that you may want to do. So when it's enabled, those last two steps are turned off. The filmic tone curve is turned off because you don't want us to do the tone curve. You want to do the tone curve. And you also have to do the output device yourself. And so the color management of that last step of you took linear, whatever it was that had happened up to this point, including all of post-processing, and now you want to display it, you can do that entirely in OCIO, and it's entirely yours. Now, here's an example of that. So this happens on a viewport, and in fact, one of the interesting things is you can have two viewports up simultaneously with different OCIOs, which is kind of neat. So that you can have one viewport set up one way where we, in fact, maybe we did this. And one of the options here is I've said I'm bringing the data from the working color space and outputting to an sRGB display with the ASUS 1.0 SDR curve. And so this does that. And then in my other viewport, I've decided to do it untone mapped. And that's just an option that was chosen in this particular config. And as it turns out, that picture down below, it's hard to see it here, but now those highlights are a little clippy. They have some orange circle around the outside. Everything is kind of not correct according to the way or not optimum to the way the original picture was, but you could still output that if that's something you wanted to do. Now, this was easy to set up. This is it. When you bring up make a brand new OpenColorIO configuration file, that object, it defaults to OCIO://default, and that gives you a bunch of things right out of the box. That wasn't the case when we first introduced it. You had to have your own file to use OCIO at all. But that's no longer the case. You can use some built-ins. And so here, I've just chosen working color space as my desired input, and my desired displays are untone mapped and ASUS 1.0. And so those are already in there. You can modify your own and do some other work there, but this is a way to get started if that's something you want to do. And then if you use that same config for writing out an EXR linearly out of Unreal, and then using that config in Nuke, then you should get the same result that you would have seen in your report, which is super handy. And so we did it. We went all the way from texture input to viewport. We got to the end. Now, it turns out I have a little bit of bonus content that I wanted to show you, which is about anti-aliasing. So I'm going to take a slight digression into anti-aliasing. So here's a picture. This is the hillside sample, and very super detailed, has a lot of geometry in it. And so let's zoom in a little ways so that we can find a pixel to look at. And in fact, we're going to look at this one. And what we're looking at here is an MRQ render using 8 spatial samples. And so that's where the anti-aliasing came from, is that we spatially sampled the image 8 times, and all that was averaged together to give us a nice representation of what's there. So how's that happen? Well, this is the grid. That's a single pixel, that big white area over there. And those red dots, those are the jitter amount that happens when we do the sampling. So if you do a normal render without this, you get a single render through the center if you use MRQ with spatial samples set to 1. But by doing this jittering, you're going to get 8 different ones. And so let's see what happens here. So, oh, and by the way, there's dark gray circles there. That's if you went to 64, and the light gray circles are if you went to 256. So it does cover the pixels nice and evenly. And when all's said and done, so if you do want to crank that number up, you can sample the scene a great deal. Because remember, the scene isn't these squares. The scene is something like this. There's geometry back there, and we want to look at that as best as we can and represent those teensy objects in our single pixels that we're trying to make. So let's zoom in a little bit further, and we can see that I added a tiny forensic object into the scene. And so that square there is 1 pixel in the final output image. So if we jitter by these red circle amounts, this is the places we are going to sample this image. And you can see that I kind of strategically placed where I put some colors into my little gray square there so that I exactly hit the ones that are in there. And there's some numbering there of 1, 2, 3 is the order it's going to be. Is it's going to be, as it turns out, RGB? So, okay, yeah, it's going to work out great. And so this is what happens when we sample. And so these are the individual samples, and you can get these from MRQ. All you do is turn on the debug options and save them out. And so you see that center pixel, it samples the red one. And then the next sample sampled the green one. And that's all it can do. It can only see one thing. It's not seeing an area. So the reason you get anti-aliasing at all is we take a bunch of single samples and then we average them all together to make a gray pixel. And that is the end of it. And so we did it. We got conversions from Unreal Engine, texture input, all the way to output. So all I ask now is you just go be safe out there.